In this lesson, we're going to continue our exploration of the electrophilic addition reactions to alkenes, focusing on additions that occur under neutral conditions. Alkenes can undergo halogenation, which is the addition of a dihalide like Cl2 or Br2. In a halogenation, regioselectivity is not an issue because the exact same group is being added to both carbons of the alkene. If we look at the mechanism, we can see that it's actually a good bit different than the reactions that occurred under acidic conditions. Once again, the alkene will serve as the nucleophile, and the dihalide will act as the electrophile. Now, when we draw out mechanisms, we tend to draw them out in sort of a linear fashion, with lots of empty space between the individual reactants. In reality, when molecules react with one another, they're extremely close, literally touching one another, in order for the orbitals to overlap. And that's important to recognize in this reaction. In the first step, electrons flow from the nucleophilic alkene onto one of the atoms of the dihalide. This forms a new carbon-halogen bond and would exceed the octet on the halogen atom that was attacked, so electrons are pushed off to create a halide. As the pi electrons flow out to create that new carbon-halogen bond, an electron deficiency starts to arise on the adjacent carbon atom. Rather than forming a discrete carbocation, a lone pair on the atom that was just attacked flows in to fill that developing electron deficiency, creating another carbon-halogen bond. The halogen atom that was attacked is now bonded to both carbons of the alkene, forming a three-atom cyclic intermediate called a halonium ion. Now we know that three-atom rings are actually quite unstable, due largely to considerable amounts of angle strain. And so it may seem strange that a three-membered ring would actually form. Formation of that three-atom ring accomplishes two things. First, it creates an additional bond that would not have been formed had the reaction gone through a discrete carbocation. Second, formation of that bond fills the outer shell of the carbon atom that accepted the lone pair from the halogen. Those two things combine to make the halonium ion considerably more stable than a discrete carbocation. Now, the halonium ion itself is still a very powerful electrophile. And again, don't be fooled into thinking that the positively charged atom is electron deficient. In this case, the electron deficiency is actually shared across the two carbon atoms in the ring. Bromine is simply more electronegative than carbon and creates a dipole, pulling electron density towards it and away from the carbons. In the second step, the halide ion that was formed acts as a nucleophile and attacks one of the two electrophilic carbons of the halonium ion. This creates a new carbon-halogen bond, which would exceed the octet on the carbon that was attacked, so electrons must be pushed off at the same time. One of the four existing bonds on that carbon must be broken. The carbon-bromine bond, by far the weakest bond on this carbon, is the most likely to break. Cleavage of that bond also breaks open the three-membered ring, relieving angle strain, and allows electrons to flow towards an electronegative halogen. The result is a vicinal dihalide, a molecule with halogens on adjacent carbons. The halonium ions that form during a halogenation can actually be intercepted by other nucleophiles. One example of this is the HaloHydron reaction. A HaloHydron is a molecule that has both a hydroxy and halogen substituent. The hydroxy group is introduced by the inclusion of water into the reaction. So here you can see that the reaction is regioselective, preferring to place the hydroxy group on the more highly substituted carbon of the pi bond. If we look at the mechanism, we can see that it starts off exactly like the halogenation. The alkene serves as a nucleophile, reacting with the electrophilic dihalide to form a halonium ion. The halonium ion can now be attacked either by a water molecule or by the halide ion that was formed in the first step. If we assume that a stoichiometric amount of water has been used in the reaction, then it's statistically far more likely that one of those many water molecules would encounter that bromonium ion before the single halide ion that was just formed. So the water outcompetes the bromide by sheer force of number. Now, as we saw in the halogenation, the more highly substituted carbon of that halonium ion is more electrophilic. And so in the second step, the water molecule attacks the more highly substituted carbon of the halonium ion, breaking open the ring to form a hydronium ion. Because the nucleophile in the second step was a neutral water molecule, an additional acid-base step is required to finish the mechanism. In this case, a weak base like water will remove one of the acidic hydrogens from that alkoxonium ion to give the final product. It's worth noting that other nucleophiles can also be used to intercept the halonium ion once it forms. For example, Reacting a halonium ion with an alcohol would result in a halogenated ether. Reacting a halonium ion with a halide would result in the formation of a mixed dihalide. Another reaction that involves the formation of a three-atom cyclic intermediate is the oxymercuration reduction. If you look at this reaction, you can see that the reagents are separated into two distinct sets. Numbers are placed in front of reagents to establish an order of addition. So here, the alkene is first treated with a mixture of a mercury 2 plus salt and water. Once that part of the reaction has completed, a reducing agent such as sodium borohydride is then introduced. The inclusion of those numbers is important. If those reagents were introduced all at the same time, the sodium borohydride would simply reduce the mercury salt down to liquid mercury and the reaction would fail. Given the complexity of the reagents, it might be disappointing to see that the reaction is simply a net Markovnikov regioselective addition of water, just like the acid-catalyzed hydration. But as you'll see, there are some distinct differences and some advantages to the oxymercuration reduction. Now, if we look at the reaction mechanism, we can see that it's actually quite reminiscent of the halogenation reaction. Once again, the alkene serves as the nucleophile, and the mercury salt acts as the electrophile. As the pi electrons flow from the alkene onto the mercury atom, a lone pair on the metal moves in to fill the developing electron deficiency on the neighboring carbon. The result is a mercurinium ion, another three-atom cyclic intermediate. The mercurinium ion is then attacked by water, again at the more highly substituted carbon of the ring, to give an alkoxonium ion, which is then deprotonated by a weak base like water. At this stage, the product still has a mercury atom attached to the carbon adjacent to the alcohol. The mercury is removed by a reducing agent like sodium borohydride, which replaces the mercury with a hydrogen. In most cases, the product formed from an acid-catalyzed hydration and an oxymercuration reduction will be exactly the same. Both reactions are simply Markovnikov regioselective hydrations. One big difference is that the acid-catalyzed hydration goes through a carbocation intermediate, whereas oxymercuration reduction does not. It involves the formation of a mercurinium ion. And because oxymercuration reduction does not go through a carbocation, it is not prone to carbocation rearrangements. And that means that reactions of alkenes that are prone to rearrangement under acidic conditions will give a different product in the acid-catalyzed hydration than in the oxymercuration reduction. So we've now seen a handful of reactions that each go through a triangular, three-atom cyclic intermediate. It turns out that all of these reactions are stereoselective, producing products from only anti-addition. As with most aspects of a reaction, this anti-stereoselectivity can be explained if we look at the reaction mechanism. We'll use halogenation as an example. The initial formation of the halonium ion can occur to place the halogen on either face of the alkene. The large halogen atom blocks that face, forcing the nucleophile in the second step to attack from the opposite side. There's also a molecular orbital explanation for this behavior. As the nucleophile approaches the halonium ion, it overlaps with an antibonding molecular orbital oriented exactly opposite the halogen atom. Either way, the result is that the two groups are placed on opposite faces of the original alkene, resulting in an anti-addition. Again, this stereoselectivity is really only relevant when new chiral centers are formed. If one chiral center is formed, the result will be a racemic mixture of the two possible product enantiomers. It's only when two new chiral centers are formed that the anti-stereoselectivity is apparent. We can draw out the correct stereoisomers for the products using the same process we employed for other electrophilic additions. In this example, we'll use cis-2-butene as the starting alkene. We take the starting alkene and rotate it 90 degrees along the carbon-carbon double bond. This enables us to draw the newly introduced groups in the plane of the drawing. Because the reaction is anti-stereoselective, only two possible stereoisomers can form. We redraw the rotated alkene without the double bond, and then add the two new groups, one on each carbon, pointing in opposite directions. So on one product, we have the bromine on the left pointing up and the bromine on the right pointing down, and on the other product, we have the bromine on the left pointing down and the bromine on the right pointing up. This gives us the two product stereoisomers with the stereochemistry explicitly drawn using dash wedge projections. And in this case, we can see that we have the RR and SS enantiomers. If we repeat the process, starting with the trans isomer of 2-butene, you'll see that we actually get a completely different stereochemical outcome. The reaction of trans 2-butene forms the RS and SR stereoisomers, which are actually the same molecule. In this case, the product is a meso compound. Regardless, we can see that we got different stereoisomers when we reacted the cis alkene versus the trans alkene. Reactions like halogenation and oxymercuration reduction are stereospecific because they give different stereoisomers for the products for each reactant stereoisomer. We've got two more electrophilic addition reactions to look at. The next is the hydroboration-oxidation. Hydroboration is the addition of borane, BH3, across a pi bond. The resulting alkyl borane can then be oxidized to form an alcohol. If we look at the overall reaction, we can see that it's another net addition of water. The big difference here is that the hydroxide was actually placed on the less substituted carbon of the alkene. Because the reaction violates Markovnikov's rule, it's considered anti-Markovnikov regioselective. And of course, that regioselectivity can be explained when we look at the reaction mechanism. The central boron atom of borane is sp2 hybridized and has an empty p orbital, and that makes it a powerful electrophile. In the first step, electrons flow from the alkene nucleophile into the empty p orbital of the borane. As the new carbon-boron bond is formed, the boron atom delivers one of its hydrogens to the adjacent carbon. The borane molecule orients itself so as to place the smaller hydrogen atom over the more highly substituted carbon of the alkene. Positioning the hydrogen atom over the more substituted carbon of the alkene reduces the steric strain that would develop in the transition state. This places the boron over the less substituted carbon of the alkene. Effectively, the first step is the addition of a hydrogen-boron bond across the carbon-carbon pi bond. The resulting alkyl borane still has two boron-hydrogen bonds. And that means that the alkyl borane can react with two more molecules of alkene, once for each remaining boron-hydrogen bond. The result is a trialkyl borane. In this structure, R represents an alkyl group introduced from reaction of a starting alkene. The trialkyl borane is then treated with a basic solution of hydrogen peroxide, which breaks the three carbon-boron bonds through a series of rearrangements. The net result is the replacement of the boron with a hydroxy group. It should be noted that because the reaction mechanism does not involve the formation of a carbocation, hydroboration-oxidation is immune to carbocation rearrangements, just like the oxymercuration reduction. The last electrophilic addition reaction we're going to look at is hydrogenation, and it's exactly what it sounds like. Hydrogenation is the addition of a molecule of hydrogen, H2. Regioselectivity is of course not a concern in the hydrogenation since the same group is being added to both carbons of the pi bond. Now if you think about it, hydrogen is not electrophilic and would not normally react with an alkene. If you bubble hydrogen gas through an alkene, all you get is a gassy alkene. The reaction only works in the presence of a catalyst. Certain transition metals, such as palladium and nickel, can catalyze the reaction. The reaction mechanism isn't fully understood, but involves the absorption of hydrogen gas onto the surface of the metal, which then binds to the alkene and then delivers the two hydrogen atoms to the pi bond. The overall result is the transformation of an alkene into an alkane. So we've seen that the electrophilic addition reactions that occur under acidic conditions and go through a discrete carbocation are not stereoselective, giving a mixture of both syn and anti-products. And we've seen that the addition reactions that go through a triangular intermediate are anti-stereoselective, giving only anti-addition products. Conveniently, the remaining reactions all exhibit syn stereoselectivity, and that includes the hydroboration-oxidation and the hydrogenation reactions. Once again, looking at the reaction mechanism can explain this observed syn stereoselectivity. If we use hydroboration as an example, we can see that both the hydrogen and the boron atom add at the same time from the same molecule, and that guarantees that they must be added to the same face of the pi bond, resulting in a syn addition. Again, this stereoselectivity is only important when new chiral centers are formed. Formation of one new chiral center will give a racemic mixture of both product enantiomers. The syn stereoselectivity is only apparent when two new chiral centers are formed. We can properly draw the correct stereoisomer products using the same process we have before. So here, starting with a Z alkene, we rotate the molecule 90 degrees along the carbon-carbon double bond. Hydrogenation is syn stereoselective, So we redraw that molecule in its rotated form without the double bond, adding the two hydrogen atoms to the top face in one drawing and to the bottom face in the other drawing. In this specific example, a single meso compound is formed. If we repeat the process starting with the E alkene, we see a different stereochemical outcome. In this specific case, the reaction forms the RR and SS enantiomers. Hydroboration-oxidation and hydrogenation are stereospecific reactions, giving different product stereoisomers for each reactant stereoisomer.